Welcome to a lesson with Dr. Powell. In this video, we will take a look at a slick proof, for why right adjoints preserve limit cones. This is not my own, but I adapted it from what I researched and saw online. And I wanted to share it. Okay, so we're going to take I as an index category, and that's going to be the index category for our limits. And we're also going to take a category S of I, which will be, we're just going to be appending an initial object to this index category. Okay, so in particular, we can, like right here, here's a diagram, just, thinking of I, J, K as being elements in our index category. L is an initial object. And we can say, well, if D is a functor that goes from S of I to the category C, we can describe a diagram in such a way as a functor that follows the index category plus an initial object. So we get a cone, right? It's a cone with the shape of I that extends back to L, okay, for a summit. So, all right, now what we're going to do is we're going to define a functor, R of D, and what this is going to do, where D is a functor that goes from the extended version to make a cone from an initial point to something of shape I. We're going to define a functor R that's going to send such a thing, D, to and restrict it to just shape I, okay? So we just remove its summit. So we're going to think of R as being such a functor. Okay, we're going to define a new limit functor that's going to involve cones. Instead of just taking a limit and getting an object, we're actually going to have a functor that's going to be working with cones. So, for instance, if we have a functor that goes from which represents a diagram of shape I, we're going to send it to the diagram that has shape S of I, where the summit is actually the limit. Okay. So, taking a look at that, we actually can see that R itself is going to be left adjoint to our new summit limit functor, that our cone limit functor, and we can see that by looking at a universal property that is satisfied with between R and the limit and this limit cone functor. And it's kind of like this. So we just need a unique, there exists a unique map that makes this diagram here commute, and then we'll automatically have this adjointness, and we'll use that. So, all right. So thinking of what this is, so we have here in green, this green map is actually denoted down here. So D, and what is D? D is basically it's a diagram with that's a cone from a summit to something of shape I. Okay, and so that's what we have D. So D of L is that's the summit. Okay, and of course the summit goes down to its diagram, which is the restricted version of it. Okay, and its map to the diagram itself actually uniquely factors through the limit of the diagram, which is right here, just the limit of that diagram. And there exists a unique map from that limit to, well, let's see for a minute here. You see, there's the map in blue. That's this map right here. I'm representing it here and here. If we take, and so imagine that we have a now remember D is a diagram of shape SI, and this also is a diagram of shape SI. And we just have a morphism between them, between the diagrams of that shape, so we have corresponding morphisms between the corresponding parts such that things commute, and that's represented here. So through that corresponding part and these corresponding parts. Well, and if we do that, then we actually have a map that goes from let's see, we have a map that goes from DL to pretty much to everything. Let's see, to the diagram here of shape E via right here, which means that we have a unique map right here in yellow by the universal property of this limit right here. So we get this unique map here just simply by universal property of limits, and that will give this adjointness. So then from that adjointness, okay, we're going to use that adjointness and this result, which we'll talk about in a second, to get to our final result of right adjoints preserve limit cones. So I'm going to explain this. This slide right here will actually come from this result. This result simply is if we have an adjoint pair, right here FG, an adjoint pair KG, then like this, and the composition of the functors going this way and this way out will also be an adjoint pair. And you can look at that by just simply thinking about adjoint natural transformation, definition of adjoints, and corresponding between, and using that to whittle this Hom set down to this one over here. And it's via these natural isomorphisms. And so we actually get the adjointness of the composition. So since we have the adjointness of the composition, we're basically done when we think about what's going on right here. We know that the lim L functor and the R functor, we have an adjoint pair right here. The F and G, now this is where we're going to start with. We're going to start with, well, let's suppose that F is left adjoint and G is right adjoint, right? So we have an adjoint pair here, an adjoint pair here, and the composition of these, and the composition GR will actually be adjoint to the composition lim L of F. And then up here we also have something similar going on. Now, looking at this diagram, we also have, let's see, F of R is actually going to be equal to R of F, if we think about what this means. So imagine that we're sticking a diagram into F, right? So a whole diagram into F, we'll get that, and it's going to end, if we pass the diagram through R, it's going to be of shape I. Well, imagine that we had something coming into F right here. Okay, so what are we plugging in here to R? Suppose we're plugging in something of shape SI, so imagine we plugged in something of shape SI over here. If we plug something of shape SI over here, we're going to output something of shape SI from this functor F, but then what is R going to do? It's going to take us back, or kind of eliminate the summit. So, and you'll see that these functors actually give you the exact same thing. So we'll use that fact to note that since we have this functor is left adjoint to that functor, and this functor right here is left adjoint to that functor, well, these two guys are actually the same. Hey, wait a minute. These two functors are both right adjoint to the same functor, which means they are going to be naturally isomorphic. So these two functors are going to be not only equal, they're going to be naturally isomorphic right here. So maybe I'll put in that natural isomorphism right there. Okay. So and there we have it. So notice that in this particular thing, notice that G, we're taking in a whole limit cone into G, and we have a limit cone of this right shape coming out of G. So we have right here that right adjoints preserve limit cones based upon the functors that we defined. Thanks for watching.